So in this video segment, we're going to look at what happens when you have more than 4 electron domains around the central atom. So if you recall, up to 4 electron domains, if we had 2 electron domains, they would orient themselves on opposite side of the central atom. So you would get some kind of an arrangement such as this. So this would be linear with a bond angle of 180 degrees. If you were to put 3 electron domains around the central atom, so now you would have an arrangement such as this, where it would be 120 degrees, and this would be a trigonal planar. And we had gotten up to 4 electron domains, which would give us that tetrahedral kind of shape. So with our wedge dash diagram, we would draw those 2 positions in the plane of the paper. We would have one position going back into the paper and one coming out. So you can imagine kind of a triangular base of pyramid there with one sticking up out of the top. Now what happens when we go to beyond that, or 5 electron domains? So if we look at our central atom and there are 5 electron domains, fitting those 5 around the central atom, as long as that central atom is below, on the periodic table, it's below the second period, so it's a larger atom, we can put that central atom in the middle. We will have 3 atoms, or 3 positions that are in the plane of the paper with the central atom, one that is going to go back into the plane of the paper, and one that will come out of the plane of the paper. Okay. Another way that might be useful to look at this is if you draw a kind of a skew triangle here, put your central atom here, and one bond one above and one bond below that. And so you can see that those 3 positions in that triangle are all in a plane. These are called equatorial positions. And the top position at the top and the bottom are axial. This is the one structure where, or this is the one situation with 5 electron domains where the positions are actually different. So the axial positions and the equatorial positions are different. And then if we go on to 6 electron domains, and we'll stop there in this segment. 6 electron domains, you'll draw a kind of a similar type diagram, but here I think what we're going to do is we're going to put the central atom and 4 positions that are in the plane of that central atom. We're going to put one atom, or one position, directly back into the page behind the central atom, and one position straight out of the page. So if you imagined a kind of a skewer that went straight into the page, so it's perpendicular to the page, and you would have one position directly behind the central atom and one directly outside of it. And again, we could also draw this from another perspective. If I draw a parallelogram with the central atom in the middle, one position above, one position below, and then bonds going out to each of the angles of that. I should put down the names of these as well. So our 5 electron domains is going to be what's called a trigonal bipyramidal. And our 6 electron domain is going to give us an octahedral. Now keep in mind that these are the electron domain geometries. If we take a look at ammonia, oops, sorry. So here we have electron domain geometry versus the molecular geometry. We have our Lewis dot structure where we have our 1, 2, 3, 4 electron domains. 4 electron domains give us our electron domain geometry, which is a tetrahedral. And then if we imagine that structure without the lone pair, we get the molecular geometry, which is a trigonal pyramidal, and our bond angle of 107 degrees. Again, 2.5 degrees in from that 109 degree that goes with the tetrahedral, because the lone pair requires a little bit more space. There's a little bit more repulsion that occurs with the lone pair than with the bonding pair. So here's a chart that summarizes all those electron domain geometries. So we have 2 is linear, 3 trigonal planar, 4 tetrahedral, 5 trigonal bipyramidal, and 6 octahedral. Now notice the bond angles also for the trigonal bipyramidal and the octahedral. Hopefully you kind of recognize this, but those equatorial positions are all going to be 120 degrees from each other, and then the angle between the axial position and the equatorial position would be 90 degrees. In the octahedral, you would have all 90-degree bond angles between those positions. We'll just real quickly go through the options for each electron domain geometry with lone pairs. So if we have 3 electron domains, we have a trigonal planar electron domain geometry. If one of those is a lone pair, we end up with bent. If it's not, we just stay with trigonal planar. 4 electron domains gives us a tetrahedral. And again, if there are no lone pairs, we end up with the final geometry of tetrahedral. No need to redraw the picture. If we have 1 lone pair, we get a trigonal bipyramidal. And again, that bond angle decreases by 2.5 degrees down to 107 degrees. Remember, our bond angle here is 109.5 degrees. And if we have 2 lone pairs, we get a bent shape. And the bond angle here then would be 104.5 degrees. Now the tetrahedral is the only one where we're going to worry about the bond angle changing due to those lone pairs. So we don't need to worry about that for the expanded octets. We go to 5. Here we have the situation where, if we have all bonds, if we have all atoms in those positions, so we have a trigonal bipyramidal. But if we have a lone pair, we actually have a choice of where to put that lone pair. We can put it on an axial position or an equatorial position. Well, given that the electron domain needs more space, we're going to put it on the position where it has the most amount of space, where there's the most room for it to spread out, which is the equatorial position. So with 1 lone pair, we end up with what's called a seesaw shape, where again the electron domain goes on one of the equatorial positions. If we have 2 lone pairs, again the electron domains are going to go on the equatorial position and make T-shaped, and 3 lone pairs would give us a linear molecule, and the 3 lone pairs would all go on the equatorial positions. If we look at an octahedral, again, no lone pairs, we would end up with just an octahedral shape. If we have 1 lone pair, since all of the positions in an octahedral are identical, you can put it anywhere you want to. But if you put the lone pair at the bottom, it makes it pretty obvious that you have a square pyramidal shape that you're creating with the molecular geometry. And if you have 2 lone pairs, now you want to consider that those lone pairs are going to want to be as far away from each other as possible. They have more repulsion than the bonding pairs, and so they're going to go on opposite sides of that octahedral, creating a square planar molecule. Okay. So these are the different geometries that you get with up to 6 electron domains. And this gets us through the majority of the molecules that we'll have to deal with.